Hello, my name is Colin Pierce. I'm the team captain. I have been on the team for 3 years.
Hello, my name is Alex Lesperance. I am an Intel operator and I've been on the team for 3 years.
My name is Brad Worship. I'm an Intel operator and I have 1 year experience on the team.
Hello, my name is Ethan Cook. I am the SREC operator and I've been on the team for 3 years.
Hello, my name is Kyle Coates. I'm the airframe handler and assistant to the safety pilot, and I've been a member for 3 years.
I'm Matthew Don. I'm the airframe inspector. I've been a member for 3 years.
I'm Caleb Fleming. I'm the autopilot operator, and I have 1 year.
I'm Sydney Shinstock. I'm the autopilot assistant, and I've been on the team for 2 years.
Hi, I'm Nathan Jones. I'm the systems assistant, and I've been on the team for 1 year.
Hello, I'm Stephen Blitz. I am the safety and communications officer, and I've been on the team for 3 years.
Our vehicle is a modified SIG Cadet Senior fixed-wing aircraft. We are using an Autopilot Pixhawk autopilot that communicates over a 900 megahertz telemetry band as well as a 2.4 gigahertz radio link for backup radio. We are using a Canon EOS M mirrorless digital camera with a dual-axis gimbal. We have an onboard Raspberry Pi that will transfer images from the airplane to the ground stations on a 5.0 gigahertz link. We also have the SREC on the 2.4 gigahertz link, and to top it all off, we have a egg drop mechanism. The mission will consist of 8 tasks, 2 primary tasks of auto takeoff, flight, land, and auto search. We will also be attempting the secondary tasks of ADLC, actionable intelligence, emergent target, egg drop, off-axis target, and the SREC. Now, we've flown this craft over 20 times over a span of 9 months. They're extremely confident in its abilities. Here are Kyle and Matt with the airframe.
As Colin mentioned, our airframe is based off of a SIG Cadet Senior model air vehicle because of its reliability, and it has proven success for this team at this competition in past years. We've designed the fuselage to be a little deeper and wider to accommodate for enough space for the gimbal and airdrop systems. The fuselage is made up of carbon fiber, honeycomb sandwich panel material, and is bonded by epoxy. We've also designed our own landing gear using a 3D CAD SolidWorks program, and I've run an FEA analysis to prove its durability. This custom carbon fiber landing gear was designed to provide enough space, vertical spacing between the gimbal and the ground, so upon landing, it will not make contact. This airframe has flown 22 times over the course of this past school year, and it has flown in last year's competition. We are fully confident in the structural integrity of this airframe.
The gimbal system is 3D ABS footed and was designed to provide greater than 30 degrees rotation in both pitch and wheel directions. The gimbal is rotated by 2 modified servos, which incorporate PID control on both axes using a gimbal control board. This board was designed in Kansas State to provide greater rotational control stability and to reduce stability issues that arose from using stock servo controllers. The gimbal system provides the image analysis team with optimal images by keeping the camera pointed at the ground at all times, unless when assisting in the off-axis target task. We tested the off-axis target task 3 times and succeeded all 3 times when pointing the camera at 30 degrees angle and pointing it toward an off-axis target. The egg drop device is also 3D ABS printed and is composed of 2 components plus a servo. A vertical component which holds the egg, and a horizontal component attached to the servo which opens when it receives a PWM command from the autopilot. We tested that 3 times as well, and we're able to succeed in variable wind conditions, and we're able to succeed in getting the egg drop to land within 15 feet of the target. With these, we are confident that we can perform these tasks well. Thank you.
For our autopilot, we use a Pixhawk board running open source ArchiPilot software. This gives us the capability to view and change the source code as needed to complete mission objectives. The Pixhawk board itself allows us to attach additional peripherals such as the LiDAR light to aid in finer control of the aircraft. It also allows us to integrate additional systems such as the gimbal and egg drop mechanism. The ArchiPilot communicates over Mavlink messaging to our ground station and mission plan, which has been customized in-house to allow us to output telemetry data to an SQL database for use in the SDLC task. In order to achieve true autonomous flight, it is imperative that our controller is finely tuned. In order to achieve this, we first had to research heavily both the ArduPilot documentation and source code. After this, we executed 10 test flights with the express purpose of tuning our control cables. After those 6 test flights, our controller was well tuned, and our plane flew well with good disturbance negation. After last year, those parameters were saved and uploaded to the new Pixhawk board for use in continued successful flights this year.
Both autonomous takeoff and landing are commanded through special waypoints and mission. To achieve autonomous takeoff, commanded minimum pitch angle is needed for the flight control. We determined this minimum pitch angle by first observing manual takeoffs and recording the autopilot curve, the safety pilot's commanded pitch angle. We then moved to testing autonomous takeoff and observed that the most robust autonomous takeoffs occurred when we used a minimum pitch angle between 17 and 18 degrees. We have completed 21 autonomous takeoffs this year. In order to achieve autonomous landing, we needed a more accurate and precise altitude measurement than just the barometer that comes on the Pixhawk board. We researched 2 laser altimeters and determined that the LiDAR light was best suited for our purposes because it has an 8-inch minimum range and provides a very smooth and reliable signal. The use of this LiDAR has allowed for a more controlled and consistent flare during landing. In addition to using the LiDAR, the team has developed a standard landing procedure that allows us to land in variable wind conditions and with different locations of airstrip. This procedure includes a downwind leg, a base leg, an approach, and a final approach. During final approach, throttle is cut at 1.5 meters, well within the range of the LiDAR, and the aircraft is pitched up 5 degrees as it skids to a land. We have completed 12 successful autonomous landings this year. With the controller tuning, the autonomous takeoff, and autonomous landing all being consistently tested and developed, we are very sure that we will be able to complete a totally autonomous flight.
We have thoroughly tested our autopilot and its retasking capabilities for an emergent target situation. We have found that it can retask in between waypoints or while loitering around a waypoint. We prefer to do it while it is loitering around a waypoint as a safer, since the autopilot loses its flight plan when a new one is uploaded. Once the new flight plan has been uploaded, our vehicle continues to its next destination to carry out its task. Some tasks that we do with the retasking are the egg drop, the emergent target verification, and our proceeding to our landing path. Up next, we have our image analysis team.
The image analysis process begins inside the vehicle. The camera is triggered using a modified Canon RC6IR camera trigger device that is hooked up to the GPIO pins inside the Raspberry Pi. The trigger is pulsed every 2 seconds to ensure an optimal number of images are taken over the search area. The camera takes the images and it is then captured on the 2.4 GHz i5 SD card, which is used because of its proven success and reliability. Once the vehicle has taken the image, we need to get it down to the ground station. This is accomplished by the communication between 2 5 GHz and 5 ubiquity bullets. The image, from the time the image is on the vehicle down to the ground station, averages about 4 seconds. With this, we can guarantee that every image we receive will be clear and quick. Once the image has been received from the plane, it will be placed into another directory and queued up for telemetry data embedding. This is accomplished by software developed in-house that queues images and queries an SQL database containing the vehicle's telemetry data using synchronized timestamps between the data and the image. With this, we can ensure that every image we receive will have good telemetry data associated with it. Once an image has been embedded, it will be placed into another directory being watched by our target recognition software, Target Site.
We use Target Site to analyze images and to complete the tasks of ADLC and actionable intelligence. We developed the software with the goals of speed, ease of use, and automation. This frees up our operators to focus on communication and mission and reduces stress in the plane. To detect and classify images, we use modified third-party open source software to determine size, shape, and color of the targets. Localization is done with embedded EXIF data in photos. We constructed our own wooden targets, placed them in a field around our test area. This gave us high degrees of success with detection and varying degrees of success with automated classification and localization. This allows our operators to have a simple task. To do actionable intelligence, we compromise between image size and image quality in order to get the image from the plane to the ground within 30 seconds of it was taken. This allows for us to act on the intelligence in a timely manner as long as doing a clear image. These considerations were also taken into account with QR code.
Our QR code software was written in-house and watches a specific image directory. Images in that directory are formatted to grayscale, and the blocks are processed to display the data. We are 70% confident in our autonomous processing, but if need be, we can switch to manual. We have tested this multiple times with first online images and then with a meter-by-meter printout. For our SRIC task, because of the upload part, we have decided to shift it towards the end of the mission to allow for flexibility in both image selection and time. We've simulated the SRIC with the 2.4 and 5 GHz connections as explained before, along with an FTP server running on a laptop computer and the exact components specified in the details. We have tested this multiple times in lab and in flight to reinforce our confidence in this proven system. I'm going to hand it off to our safety officer.
Here at Team SpyCat, we strive to improve our own safety culture. We comply with FAA, AMA, and AUVSI seafarer safety regulations. At any point in time during the mission, our safety pilot may take control of the plane. He also has control of the return to home functionality. The return to home functionality will trigger automatically in the event we lose RC connectivity for more than 30 seconds. If after 3 minutes we can no longer reconnect to the RC, the autopilot will terminate flight. We use a series of pre-flight checklists to ensure that mission-critical tasks are completed in a timely manner. This allows us to have a very clear and very concise go and no-go conditions, which you can find a condensed version of on the back of your safety pamphlet. We also use very good communication skills. We have implemented this year a series of headsets which allow us to communicate very quickly over the course of the mission. For example, our safety pilot is off in a safety radius of about 3 to 5 meters and is not with the rest of the team. So this headset provides very good functionality in that nature. This also allows the team leads to communicate with the flight director and the airframe inspector. We have a very clear chain of command in which any team member will go to their team lead, and if escalation of the issue is required, it will then go to either our safety pilot, our flight director, or our autopilot members. Without further ado, here is our flight director for a closing statement.
In this presentation, we've provided evidence of mission accomplishment. We've also described the planning, evaluation, and testing of our system. All members on the team are very knowledgeable of the system. And the flight line consists of veterans who have learned from previous members on Team SpyCat, as well as novice members who will carry on this knowledge into the future. We are very confident as a team, and our successes show that throughout the testing this year. And I think we will be very good this year in competition.
Now we're going to take 5 minutes for Q&A.
For the imagery,
we were flying, we were out kind of in a park, and there's a lot of like storage buildings out there, so we received a lot of false positives based on that. So we haven't really been able to fly in a huge open field like we have available here. So a lot of our false positives come from our vehicles and storage sheds.
We did have quite a few.
Yes.
Yeah, that's shown basically on the board here when you come up for the static display. We have the number of times we have completed each task.
Do you guys do any modeling and simulation?
Yeah, for the landing gear, we did some FEA analysis, so we drew it up in SOLIDWORKS, put it on there, and then we put like a 20-pound load on it, drop it, and 1 meter drop it. It's well within the ranges. Yeah, it's proven to be well, and we have not had it break or anything in any landings in our 22 classes.
Good.
Your flight termination, if you could explain.
Yes. So, detailed in the rule in Chapter 9, I believe it's Section 356. What we have to do is we basically go into this spiral. It's a very controlled, very low speed spiral. And we set the home location away from where we are because with actual AMA regulations, you are supposed to have a safety line from which no personnel passes. Due to the nature of this competition, that is a very hard thing to achieve, just based off of how large the field is and all the objectives we're flying. So we have the home location a far enough distance away that when we do have to crash the plane in the event of an emergency, it crashes away from personnel. And it also has very bright colored wings, so in the event that it does go down, everyone can see it. We'll be communicating that it's going down. We have a trailer in the event we need to take shelter. And so essentially what happens is, and the autopilot can back me up on this, I believe, we have the elevators go up, rudder pull to the right, correct? And we just cut the throttle. And so it'll go into a nice little spiral and eventually land, hopefully without damaging the plane. Does that answer your question?
That's fantastic.
Yes.
I guess I've got the autonomous. What you just mentioned there was about having some control of the aircraft. In this case, you have lost some control. You can't really return it home.
If we lose GPS, yeah, there is a fail-safe for that.
If we only lose GPS and we still have RC though, our safety pilot has landed the plane on numerous occasions and we're confident in his ability.
So how many of the targets that are out there? All of them. How confident of you are of that?
Last year we found all of them. We used a less than desirable camera, and so although we didn't find all the targets, we were able to classify them. I am equally as confident.
Any other questions? Thanks, guys. Appreciate it. Judges, so what we have Q1, what we have good team of judges, we right over there. Let me go ahead and start listening.
Yeah. I don't know if there was actually 35.